All right, so let's talk about question number 8. So here's the setup. So the basic idea is that you have a bungee cord like this, okay? So when you jump off the bridge, you fall for a while where the only influence is gravity, okay? And so you're gonna fall for a certain distance just in free fall. You jump off there, nothing's happening, there's no bungee cord, it's just like you were just falling. So what's gonna happen here, so if you look at that information, so you're told on that one, however they're gonna fall, however distance they're gonna fall, 12 meters, okay? So they're gonna fall 12 meters before the bungee cord even begins to stretch. So that's just old school kinematic equations. You know, the initial velocity, you know, the final velocity, or you're finding the final velocity, you know the acceleration, you know the distance, just use that equation, okay? There you go. Now, when you get to the second part, you want to calculate the spring constant. So here's how you want to visualize this, okay? So this person is falling, they're going to hit the end of the bungee cord, then that bungee cord is going to begin to stretch, okay? So at some point, they're going to be all the way down here. So here's the relationship that you want to look at, is that the potential energy that they have caused by gravity, by being this far below the bridge, has to equal the energy stored in stretching the spring, okay? So when they're at the bottom, so the UG that they store, okay, so imagine that you've got to lift this person up to a height of 31 meters, okay? So the UG here has to equal the potential energy that was stored in the spring. Because if you could take that energy that was stored in the spring, that would shoot them all the way back up to the top. So then you can go, okay, hey, that's MGH. This is 1/2 kx squared. Okay, so what you're searching for is your spring constant, which is going to be that value of k. So nothing can cancel out, but the trick here is the numbers. This h has to be that 31 meters, which is how far they are below the bridge, okay? Because that's like if you reverse the process and you took them down here and you lifted them up, that's the change. That would be the change in the gravitational potential energy. So that h has to be the 31 meters. Your x is how far the bungee cord gets stretched, okay? So they fall for 12, then this begins to get stretched, so that x is going to be 19. So you're going to know everything except for that value of k. And so if all goes well, your value of k should be around 100, okay? So that answer to 8C should be around 100. Because if that's wrong, kind of everything else turns into a train wreck. So then, you're going to say, okay, well, let's look at this from a force standpoint. So as that bungee cord gets stretched, there's more and more and more of that force acting upward gets bigger and bigger and bigger. Because the upward force from the bungee cord is going to equal F equals Kx, okay? Well, you're not going to change K because that's the spring constant, okay? So the farther that stretches, the more force there is acting upward caused by the bungee cord. So at some point, you're going to create an acceleration. That's the whole point, is that you want to accelerate. You want an imbalanced force. You want that upward force from the bungee cord to be bigger than the gravitational force acting down. Because if this force upward never gets bigger than the downward force of gravity, you're never going to stop, okay? You will always continuously accelerate downward, okay? So at some point, this has to be bigger than the force of gravity, or you're not going to stop, okay? That's just the reality of it. So the whole key to this is when you get to D, where it says, hey, all I want you to do on D, do not make D complicated. All I want you to do is write an expression for the idea of the net force. Oh, the force of the bungee cord acting up is a value, and then you have the gravitational force acting down, so that your net force is just going to be the difference between those two. So all you have to do on 8D is write, oh, force net equals force of the bungee cord minus gravity. That's it. That's all you have to do. Okay, you don't have to plug in numbers. All you're doing is just writing the expression. Okay, that's all you're doing. Now, when you get to E, then you're going to calculate the actual acceleration. So when you get to E, you're going to go, oh, force net equals force of the bungee cord minus force from the spring. Okay? Now, Yankee, at the end of the day, what does any net force equal besides the difference between two other forces?
Zero.
No. You don't want a net force equal to zero or you won't stop. What's the other way that you can express net force? It's written on that big sign behind you.
Oh, F equals ma.
Mass times acceleration, right? So you can find the force from the bungee cord because you know that's kx. You know the spring constant and you know how far it gets stretched. You know what, that's the force from gravity. You know that mass and you know the gravitational acceleration, so the only thing you don't know is A. So if all goes well on E, you should get an answer something close to the legal drinking age. Not what you think it is on prom weekend. Got it? Now, let's talk about number 9. There's two ways that you can work number 9. One's very complicated and one's very simple. So the complicated version is that you go old school kinematic equations. And you're launched at a certain velocity and you find your Vy and you find your Vx, okay? And the whole key to this is that they want the speed when it lands. So you've got it, you're going to find the vertical component of this velocity. You're going to find your maximum height using that equation. And then you're going to use that equation again to find the final velocity when it lands. So you're going to use this, you're going to find your maximum height. You're going to use this again to find your vertical velocity when you land. You know your Vx, so then you're going to take your Vx and that new Vy and find the hypotenuse of this. So here's option number 1. If you like trig and you like old school kinematic equations, okay, this is in your wheelhouse. You know this angle, you find the x and you find the y components. You find your maximum height, and then on the way down it starts at 0, so you know your initial velocity, you find your final vertical velocity. When it lands, it still has that same Vx, so you know your Vx. Make sure this Vy is bigger than that Vy because it's falling a long way, okay? And then you find the hypotenuse. So if you like old school, Mr. Rickham, I love problems like this. I love kinematic equations. I love that equation. That's how you're going to work the problem. Okay? Old school, it works. It's great. It's fantastic. It works. Okay? That's option number 1. Option number 2, you go, Mr. Rickham, I like energy. Oh, okay, that's cool too. So when this thing is launched, ray gun, you're above the ground and you're moving. So what 2 types of energy do you have?
Potential and kinetic.
Yeah. So the kinetic energy at the top, plus the UG at the top. Now, when it lands, what's the only type of energy that it has, ray gun?
Kinetic.
Yeah. It only has kinetic energy at the bottom. Okay? So this is going to be your initial kinetic energy, and it doesn't make any difference which angle you throw it because this is a scalar quantity. I throw it horizontally, I throw it straight up, I throw it at an angle, doesn't make any difference. It's still going to have the same amount of kinetic energy. It's going to have a certain amount of UG because it's above the ground, and then it's going to land with some final kinetic energy. Oh, okay. Put in the numbers. All right. So that's 1/2 mv naught squared plus mgh equals 1/2 mv squared. Now, conveniently, the masses are the same, so what can you do with the masses? Cancel them out. This is why I didn't give you the mass, because you don't need it, okay? If you're really hard up, like, oh, Mr. Workham, I actually want to calculate it. Great. Let the mass be 1 kilogram, okay? I don't care. Pick a number. Or you can just cancel it out. So you're going to know this initial velocity, you're going to know the h. What you don't know is the final velocity. So this is easier because you don't have to go through all the rigmarole of finding the x and y components and then recombining them into a new one. And if you simplify this, all of this is, if you simplify it and you multiply everything, you just get that equation, okay? Or you can just use that equation right from the get-go, okay? That's your other option, because that equation comes from the idea that you have potential and kinetic energy. So, anyway, if all goes well on number 9, you should get an answer around 200 meters per second. On number 6, because if 6A is wrong, everything else is going to be wrong. That answer for 6 should be 2 joules. And I'm going to tell you right now, on especially one like number 6 or number 7, if I don't see a chart and as soon as I see the first wrong answer, I'm done grading at that point. Okay, I'm done. Okay, if you don't want to set up a chart, that's fine. If you don't want to work it the way I want you to work it, that's your choice. You all are big people. But here's the consequences. I quit grading. I'm not going to sort through random things to try and guess what you've done. Okay? So if you don't want to set up a chart, fine. You all have to make decisions. But then I quit grading. Okay? And any points beyond that, I'm not going to correct what you have. I'm not going to waste my time trying to sort through it. I'm just done. Okay? So that's a decision that you all need to make. Your answer to number 7, that first answer on A, would be a fairly respectable GPA. Not horrible, certainly a lot worse, but not all that good. And if your spring constant on 4A is wrong, everything is going to be wrong. So that answer to 4A should be around your current age, probably a little bit higher than your current age. Okay. Anything else on that assignment? Elliot, talk to me.
6B.
Where you want to find the energy?
Yeah.
Well, all you're doing is just changing forms, okay? So here's your chart, okay? And you can have kinetic energy, and you can have us, and you can have the sun, right? So everything has to add up to 2 joules. So if you can figure out how much energy that you lost using 1/2 kx squared, subtract that out, and that's whatever's left. So your answer to 6B has to be less than your answer to A. So if you can figure out how much energy has been transformed into something else, subtract that from 2 joules, that's what you have left. Because everything has to add up to 2 joules. So your answer to 6B should be around 1.9 joules. That's an ish, but it's somewhere around there. Because everything has to add up to that total amount of energy. Okay? Does that answer that, Elliot?
Yeah.
Okay. Anything else? Going once? Going twice? So, what you're going to do, it's kind of cool because it goes like old school. It actually, so it kind of goes retro back to the very first lab that you all did in this class. And if you harken back to those days, and you all drew a graph, and we hung weights from the end of the spring, and we measured how far it got stretched, right? And I said, oh, you're going to multiply a number by 9.8 meters per second squared. You know, like, okay, whatever, it's physics, we'll use 9.8. And now you know the significance of that 9.8, and that's the acceleration caused by gravity. And at the time, when you all did that lab, you put force along the x-axis, and you put elongation along the y-axis because force was your independent variable, and that's what you were manipulating. And you put elongation on the y-axis because that was your independent variable, or your dependent variable. And your elongation was dependent upon force, and you drew the little line, and you best fit, and all this good stuff, okay? Well, now we're going to kind of revisit that idea, but now we're going to look at it from a different perspective. So the first thing that you need to do in this lab is that you need to find the spring constant. So to find the spring constant, we need to change this up to make the units work out. So with this one, you're going to put force on the y-axis, and you're going to put elongation along the x-axis, okay? So first off, that's the first thing that's got to happen. You've got to change these axes. So on the diagram at the bottom, it actually shows like a hook, okay, for support. Don't do that. You want to use like a rod and hook that spring up through the middle of that. That way you'll be able to adjust that exact position. So all the top rod is doing is just holding that in place. You want to set the next ring down so that the bottom of that ring is level with the bottom of the hook. So all this is going to do is to serve as a visual reference for where the bottom of the spring is. Okay, so that's what we're going to say, okay, at that point, this is where the bottom of the spring is, because that's going to allow us to measure back to that point. So you're going to hang different weights from the bottom of the spring. Okay, so the first one is going to be 400 grams. Okay, so you can hook that up, and you're going to measure how far that stretches. Okay, so measure from the bottom of the hook back up to the bottom of that ring. So the first thing that you're going to do is you're going to try and find the spring constant. So you're just going to hang different weights from the bottom, and you're going to measure how far it stretches. Now, make sure that you put a clamp on here, because otherwise with the weights that we're going to be putting on there, if you don't, this thing is going to fall over and it's going to make a god-awful amount of noise, and it's not going to end well. So make sure that you put a clamp on the table. So you're just going to hang those different weights down. So help me if you ask me how to calculate weight, I am just going to completely blow a gasket. Okay? So what you want to measure is elongation. Okay? Make sure that's in meters. So again, your elongation is not the total length, it's how far it stretches. So you can take it, measure it, boom, first thing you do is find that. So when you draw this graph, you're going to have points along here, okay? And odds are these aren't going to be exactly linear, okay? They're going to be pretty close because there's something known as Hooke's law, okay? But you're going to come in here and you're going to draw a line of best fit. So, and I tell you this, in the instructions, you're going to come in here and you're going to circle the points that you're going to use to find the slope of the line, okay? Because everybody's slope is going to be different depending upon which spring that you have and how you draw your line of best fit, okay? So circle these, say, oh, here are these data points, okay? That's the first thing I want to look for. Now, you want to find the slope of the line. If you want to show the calculations on the slope, that's cool. If you want to show it below in that space, cool, knock yourself out, okay? Just show me how you found the slope of the line. And do not leave that slope as a fraction, so help me, I will blow a gasket again, okay? Do not leave that slope as a fraction. This is not a math class, we actually need decimals. So typically that slope on these springs is usually between 65 and 75, okay? That's an ish, but that's generally about where that's going to fall. Now, when you get to number 3, listen to me very carefully on what I want on number 3. So you're going to find that maximum elongation, okay? And that's why I've got a little asterisk on the end of that, okay? This is going to be like the cornerstone of a bunch of calculations that you're going to do later on. You've drawn your line of best fit. you're gonna go to that maximum elongation. I'm just gonna say that maximum elongation is 0.22 meters, whatever yours is, okay, whatever yours is. So this is what's gonna be vital because you're gonna use that number later on. You're gonna find that maximum elongation and you're gonna draw a line straight up to where it crosses that line of best fit, okay? Not the data point associated with it, okay? Not the force, with where it crosses the line of best fit. Then, I'm going to tell you, circle that point and write the coordinates on the graph in the space below. So you're going to have this line of best fit. You're going to go to your maximum elongation, whatever that is, and you're going to go straight up. And you're going to find out where that crosses this force, and that's what you're going to use as that data point later on to do some calculations, okay? So come over here, straight up, see where it crosses that. Now, if that happens to be the force associated with that, hey, great, okay? So winner, winner, chicken dinner. Odds are it's not, okay? So it's going to be wherever it crosses this line of best fit. Write down that coordinate because you're going to need that later on to do some calculations. Okay. Now, after you get done with that, now you're going to need the lower rings. So over on page 2, you're going to hang different weights from the spring. So you're going to hang 1.2 kilograms. Okay. So imagine that's 1.2 kilograms. It's just 1 kilogram, but you get the idea. Okay? Now, here's what you're going to do. And this is why you have to be able to adjust the alignment. So what you want to do is you want to get this thing oscillating back and forth. Now, get it oscillating, and then what you want to do is you want to set the rings at the top and bottom of the oscillation after it's oscillating. So what I don't want you to do is don't pull it down to this point and then let go of it. That's not it, okay? You want to pull it down, get it oscillating, okay? And then watch where it's going. And this is why you have to have it exactly in the middle. And then you're going to set the bottom ring at the bottom of the oscillation, and you're going to set the top ring at the top of the oscillation. So you just got to watch it going back and forth like this, okay? So you're going to do that a total of 3 different trials. The first one with the 1.2 kilograms kind of have a smaller, what we call amplitude, okay, which is how far it moves. So you're going to get it going like this. You're going to set those points. Now, you need to measure 3 different distances, and these are on the front of the lab, and I've also got it drawn here. So basically what's happening is that this is just a transformation of energy, right? So this thing is oscillating back and forth. Tanner, is the weight changing directions? Yes. Where does it change the direction? Top, bottom of the top, right? So this thing is oscillating back and forth. You're changing directions, right? So if you look at this from a kinetic energy standpoint, at the top and bottom, it has no kinetic energy because that's when it's going to change the direction. Oh, okay, right. So if you have no kinetic energy at the top and you have no kinetic energy at the bottom, where do you think you're going to have your maximum kinetic energy? Ray gun. I have no kinetic energy at the top and I have no kinetic energy at the bottom. Where do you think I'm going to have my maximum kinetic energy?
In the middle.
In the middle, okay? That's when I'm going to have my maximum kinetic energy, okay? Because as soon as it crosses the middle, so it's going to speed up till it hits the middle, and then it's going to start to slow down, okay? So that's one type of energy that we have is kinetic energy. That kinetic energy is always changing because our velocity is always changing. Now, Rebecca, what's another type of energy this thing is going to have?
Potential energy.
What kind?
Spring potential.
Okay, is the spring potential energy changing?
Yes.
Why?
Because it's changing elongation.
Fantastic. Okay? So the potential energy in the spring is also always changing because we're always changing the value of x. Now, as this thing oscillates, when do you think it has its, Elliot, when do you think it has its maximum energy stored in the spring? At the top or at the bottom?
The top, the bottom.
Bottom. Because if you look at the equation for us, that's 1/2 kx squared. So when the spring is stretched to its greatest length, that's when you're going to have your maximum us. Okay? So you're going to have your maximum us when it's at the bottom. Okay? So there's a second type of potential energy. Kyla, what's another type of potential energy we could have?
Gravitation.
Yeah, we could have UG, right? So UG is changing because the height is changing, right? Now, you have your maximum us at the bottom because that's when the spring is stretched the most. You have your maximum UG at the top because that's when it's highest above the ground, right? So if you look at this in terms of containers, this is actually a 3-container system. You have UG, you have us, and you have KT. Okay? And so all you're doing is continuously changing the energy within the system. Now, we actually have a 4th container, and that's thermal energy. Okay? So when this thing oscillates, it's kind of cool, like if you think about it on an atomic level. So within that spring are nuclei, a lot of iron atoms, okay? Pretty dense, massive nuclei. It's got these electrons that are going around it, right? Okay, you all studied chemistry. You got this visual. But what's cool about this is that when you stretch these particles, they have like a memory. And they go, oh yeah, we want to go back. So when you get that thing going, the reason that this thing oscillates is that on an atomic level, these atoms are getting stretched apart. They go, man, I'm not digging this, okay? So collectively, they make a decision that says, we're going to go back to the way we were. And that's what allows this thing to oscillate. So anytime you have particles moving past each other, it generates heat, okay? Which is why when it's cold, if you rub your hands get warm. So on an atomic level, these atoms are vibrating. They're moving past each other and they go, oh, man, this sucks, okay? And they're not liking it. So they generate some thermal energy. So this is why this spring stops after a period of time. If we weren't losing energy to thermal, this spring would, you could come back at the end of the day. I could get this thing going, and you're getting ready to leave at the end of 4th block. You could, peek your head in, okay, and check, and that thing would still be oscillating back and forth, okay? If we lost no thermal energy, that spring would just continuously go back and forth. You could stop in tomorrow, you could come in tomorrow morning. It's still going to be going back and forth like that, okay? Which would be cool to see, don't get me wrong. But we're going to lose some to thermal. Now, don't think, when you do this, notice that I did not put a caution at the front of the lab that says, oh, caution, spring may be hot, okay? It isn't like, wow, I need to start a fire. I'll stretch the spring back and forth, and that'll generate some thermal energy, and I'll light some paper on fire, okay? Or you don't have to worry about grabbing spring. Oh, man, that's hot, okay? We're not generating that much. But it is enough to make that slow down over a period of time. So if you're ever out in a forest and you have a spring, you think, oh, I remember Bergkamp's lecture on thermal energy. I'll stretch the spring back and forth and I'll start a fire. No, it's not going to happen. But it is going to dissipate some of that energy. So on page 2, you need to measure 3 different values. And I've got this on the front of the lab. So X1 is going to be from that equilibrium ring down to the first ring. Okay, so that's going to be X1. So if you think about it, that's how far it's stretched, and that's how much potential energy we store in the spring when it's at the top of the oscillation. X2 is from here all the way down. So X2 is going to be the biggest value, okay? So X1 is from here to here. X2 is from this ring down to here, okay? That's X1, that's X2. You're going to use that to calculate the energy stored in the spring as it oscillates back and forth. Now, H is going to be the distance from this ring to this ring, because that's how much gravitational potential energy changes as it oscillates between these 2 points. So you're going to have 3 different measurements. X1, X2, okay, and then H. The biggest one is going to be X2, the second biggest one is going to be X1, and the smallest value is going to be H, okay? Now, then, down below, you're going to calculate the potential energy stored at X1. So at this point, you're going to know the spring constant, you're going to know how far it stretches, you're going to calculate the potential energy stored there. Then you're going to calculate the potential energy stored when it goes all the way down to the bottom of the oscillation. And then you're going to calculate the change in that value. Okay, you're going to know one value, you're going to know the other, subtract them out. And then you're going to calculate the potential energy stored as UG. Now, down below, I don't need to see all these calculations. I only want to see the calculations for trial 1. Okay? Now, when I say show me the calculations, I don't mean just write down the formula. I know what the formula is. I want to see those calculations done with your numbers, okay? I want to see 1/2 kx squared. I want to see 1/2 times your k times x1 squared, okay? And when I say show me the calculations, I'm not saying just write down the answer. I want to see how you calculated that value, okay? You're going to put the answer up above. You don't need to write down the answer again. All I want you, like for that trial 1 where it says U1, I want to see 1/2 times the spring constant times x1, okay? That's what I want to see, okay? I don't write down the formula. I know what that is, okay? I want to see the calculations. All right, then you have a bunch of questions to answer. So I cannot emphasize this enough. On this graph, you have an entire sheet of graph paper, okay? Draw this graph as big as you can. You don't have to have the graph done to get all of your data. Like the graph isn't dependent upon this, okay? So when your 3 trials on page 2, first trial, you're going to do kind of a smallish amplitude. Trial 2 is going to have a bigger amplitude. Trial 3, you're going to put 1.5 kilograms on there and do that. So you're going to do 2 trials with 1.2 kilograms and third trial with 1.5. Watch it oscillate, measure your distances. All right, ready, break. Here we go. So if you want to plan your week, so we've got this lab today. Tomorrow we're going to do rotational kinetic energy. Wednesday we review. The test/final is going to be on Thursday. And then we start a 3-day lab final Friday, Monday, Tuesday. Okay? So that's how that's going to play out. All right, let's go.